Hello, my name is Kasey Berger and my partner is Tom Chelman. And today we'll be presenting on X-ray diffraction and residual stress. So what are residual stresses? Residual stresses are tensile or compressive strains within a material or component when no external loads or forces are applied. Residual stresses can develop from various manufacturing processes such as forming, forging, rolling, welding, or machining. So there are also microstructural examples of residual stresses. For example, in age-hardened alloys, you'll have precipitates. When they're sufficiently small, they'll have coherent interfaces, which will result in strain fields in your matrix material. You also have substitutional atoms, which are larger or smaller than the atoms in the surrounding lattice, and that can generate local strain fields as well. You can introduce compressive residual stresses at the surface from shot peening, for example, and typically we use residual stress measurement by X-ray diffraction to measure stress around cracks within different phases in a sample, crystalline thin films, welded joints, and thermal barrier coatings. So residual stress is measured by X-ray diffraction by relating stress and Poisson's ratio to the lattice spacing. A stress on the lattice is first assumed to be planar. Due to Poisson's ratio, there'll be a change in d-spacing of the lattice perpendicular to the planar stress. By measuring the d-spacing normal to the surface of a specified crystallographic plane and then again at another angle, the change in the d-spacing of that plane can be used to calculate the residual stress. And that'll result in a peak shift in the diffraction pattern. So as you can see here, you've got your d-spacing, which is related to Poisson's ratio and your modulus of elasticity. At the red arrow, you can see the d-spacing of the 311 plane with no stress, and you can estimate that by using the relationship shown in the chart. And then something else to note is that since the technique is differential, you don't need an unstressed sample as a baseline to calculate the residual stress of your sample of interest. Here's a typical example of the experimental process. This is the constant time method. So you'll test your sample with a starting psi of 0 and make a preliminary scan. And you'll determine your peak position for your chosen Miller indices for that 0 condition. You'll apply Lorentz correction factors, find your peak position of the corrected data, and then repeat steps 3 through 5 for your second psi, whether you decided it was 30, 45, or 60, which are the most commonly used angles. And then you'll solve for the stresses using the equations to the right. Some additional information on sample requirements. Typically, you'll need minimal texture, and it'll be a polycrystalline sample with small grains. The surface of interest can't interfere with the incident or diffracted beam, therefore some sectioning may be required. And something you need to consider with that is if by cutting your sample, you'll be introducing any stress relaxation. Ideally, your surface will be smooth with minimal pitting. And then in some cases, you'll need to establish an empirical relationship between stress, d-spacing, and psi for the material of interest. And sometimes you cannot assume that the elastic constants of the bulk are going to be representative of the surface where your measurements are being taken. So that's something else to consider. Additional limitations. Measurements are made initially assuming that there's no stress in the direction normal to the surface of interest, which might not be true. And this highlights the benefit of plotting d-spacing versus sine squared psi. And if these two do not share a linear relationship, there might be other factors impacting your sample. Measurements are made by determining peak shift, and thus peaks used for measurement must be easily observed and distinct. And the irradiated area cannot extend through curved regions, so your sample should be flat, despite the fact that a lot of the times the areas of interest for residual stress occur in bends or at roots of threads, for example. And then if your sample will fluoresce, that can contribute to error or noise during your measurements.
Okay, so here are some applications of measurement of residual stress in arc welded lap joints. The tensile residual stress caused by welding is harmful for fatigue strength, corrosion resistance, and other mechanical properties of welded joints. So it's for those reasons that Lin et al. Investigated the stress distribution of residual stress caused by welding of lap joints on thin steel sheets. Lin et al. Utilized the cosine alpha method of X-ray diffraction for their analysis. This method differs from the more typical sine squared psi method. The cosine alpha method is based on distortion of the Debye ring, which is a diffraction ring in the area of the sample surface exposed to X-rays. The results of this study show that the longitudinal residual stress near the weld is tensile and close to the yield strength of the base metal. The residual stress was almost uniform along the welding direction. The distribution was almost uniform along the welding direction. The welding residual stress in the arc welded lap joints are significantly influenced by the strength of the base metal and the welding heat input. Another application for use of measurement of residual stress is in thermal barrier coatings. So residual stress generated during manufacturing is a common problem, especially for layered structures such as coatings. These residual stresses are closely related to the failure and lifetime of the component. It's very important to measure the residual stress distribution in these components. Lee et al. Conducted a study to calculate residual stress values from diffraction patterns at increasing depths in the thermal barrier coating. Thermal barrier coatings are typically made of yttria stabilized zirconia. However, due to the high absorption in zirconia, the penetration depth of standard lab-based X-rays is typically too small to measure the stress in the interface region. Since a high-energy monochromatic beam is needed to produce suitable penetration depth, a synchrotron X-ray source was actually chosen for this experiment. The residual stress values were found to be compressive and increasing from the surface to the middle layers of the coating with a non-linear trend. Residual stress values were found to correlate to crack distributions found in the samples. So they found good correlation with their test results. The study concluded that the driving force for generation and propagation of cracks is believed to be residual stress in the coating, which originated from mismatch of the thermal expansion coefficient between the top coat and the thermal expansion coefficient of the substrate. Stress remains in the thermal barrier coating after cooling due to the constraint of the substrate. One last application in measurement of triaxial residual stress. A method was proposed by Tanaka utilizing several Debye rings taken at different incident angles of X-rays in order to determine triaxial stresses. Since the penetration depth of X-rays is shallow, the stress state is usually assumed to be biaxial. However, in some cases, out-of-plane stresses are not negligible, and triaxial stresses need to be considered. Cosine alpha method was applied to measure triaxial residual stresses of unidirectionally machined surfaces of carbon steel made by grinding, milling, and planing. The cosine alpha method is simpler and quicker than the sine squared psi method for triaxial stress analysis. So it was determined that out-of-plane shear stress along the cutting direction was characteristic of unidirectionally machined surfaces and increased with cutting severity in the order of grinding, milling, and then planing. Shear stresses in the YZ and ZX direction were precisely determined by cosine alpha and sine alpha diagrams measured under normal incidence of the X-ray beam. The in-plane normal stress was compressive for ground and milled surfaces, and the magnitude of compression was larger in the direction perpendicular to the cutting direction. Magnitude of in-plane normal residual stress was suggested to increase near the surface. So
And
again,
here
here's
are
a list of our sources for our research and presentation.
Thank you very much.